most n minus 1 choose 2k minus 2 ways, we can cut up to 2k minus 2 edges from T. And it is not hard to generate these systematically in these times, in constant time, per partition. And in this article, of course, is inspired by the work of Nash-Williams in 1960, I think, that results that the maximal number of disjoint spanning trees of a graph is at least half the size of the min cut. So Nash-Williams in 1964 said something, and in 2000 or 1996, Karger was interested in this article, and in 2008, of course, from 2000 till 2008, Michael Thorop were interested in that, and I will explain in 2018, Chandra Chikuri just summarized them and introduced a new optimization approach, very simplified approach to these ideas in order to make it more powerful. And even in 2020, people like Gupta, Anupam Gupta, uses the ideas of these ideas, but in a different ways. Personally, I like the work of Chandra Chikuri, also Michael Thorop, and because all of them are using the idea of Karger, which is based on the mathematicians like Nash-Williams, and so this is the process of developing this science. So the article is inspired by Nash-Williams, which results that the maximal number of disjoint spanning trees is at least half the size of the min cut. For example, you have the number of disjoint spanning trees is 1. For example, the size of my min cut is 2 because this is 2. And for example, here are lots of clicks here. And the size of minimum cut is 2. So the number of disjoint spanning trees is 1. It goes here, after some time it goes, but it never close the loop because spanning tree is not a loop. So let's talk about another important things, which first of all I should say that min cut is an upper bound. So it's a two-factor approximation for min cut. So the weight of a tree packing is a true approximation for min cut. Remember the work of Naur and, of course, Joseph Naur, not Asaf Naur. Joseph Naur and Yuval Rabbani for K-cut. Beautiful things like this optimization. S of E is the weight of an edge, and D of E is just the usual. If it is 1, it means there is an edge. If it is 0, it means it is not an edge. And subject to the constraint that D of E is greater than K minus 1. So at least K minus 1 of one of them is connected. So imagine like this. So K minus 1 of them, for example, is K3. We have two of these lines, 1, 2, that they are connected. So it's a spanning tree, and we solve that. But we want to show that trees will cross any given K weight cut less than 2K minus 2 times on average. So instead of using those LP solvers that you use in Python, we use the greedy tree packing. So we give each tree a weight, which is its multiplicity divided by maximal edge utilization. And let's say pi is the probability distribution over spanning trees. And the cut ratio is just C of GP, the usual things. And relative load that I told you, which is L of pi of E, which I said it is the number of trees having E divided by total number of trees. So it's like a probability that an edge is inside this tree. Of course, T is a random variable because it is drawn by your probability distribution pi. And we define the weight of a tree to be probability in P divided by maximum utility. Oh, I should say what is maximum utility. Maximum utility of pi is just the maximal utilization. Maximal utilization of an edge. So my spanning tree must have at least p minus 1 edges. So your relative load of an edge should be greater than or equal to p minus 1. So I just write the same thing, the same argument that I've told you before, that Lg over P is just, I'll repeat it just because it is important. And U pi of E, C of E. So this is less than, as I said, because this utility is less than maximum utility of E. So this is less than max util times C G over P. Because this one is less than that. And now we are ready to say the cut ratio. So the cut ratio by definition is just CGP divided by P minus 1. Because this is greater than CGP over, now we can see the inequality. Util of P pi CG over P. And this goes with this. So what is left is just 1 over maximum utility of pi. And so there exists a partitioning P star such that your cut ratio is equal to 1 over maximum util. These are the arguments of Michael Thorop. But the general algorithm of Michael Thorop, general algorithm, it's very abstract because you can make it any way you like. So first, the P star is the partitioning, using spanning trees, of course. Partitioning such that cut ratio of P star is equal to maximum util. We take the cut ratio to be maximum util of pi star. And in the second step, for all edges in E of G, we set the utility of the edge to be 1 over cut ratio of P star. And the third step, for each set that I say, for example, A, that is in your partition, for example, it could be one of the clusters, we recurs on the subgraph G induced by A. So remember that A is picked very randomly from your P star, which is, for example, let's say A1, A2, those things. And of course, this is just the beginning of these ideas, because, this is an idea of David Karger. But nowadays, as I said, Anupam Gupta, for example, in his work in 2020, he talks about middle size cut. And he wants to be as linear as possible and reduce those small cuts. And that's another idea. But personally, I like the work of Chandra Chikuri. Very beautiful work. You should read the work of Chandra Chikuri, 2018. Also, Jason Lee is very in CMU, Carnegie Mellon, I think. It is very interesting work. And Thorup itself, who was the first person, I think, who discovered in 2011 that it is fixed parameter tractable. Good news for those guys who work on fixed parameter tractability and those deterministic algorithms. And also the work of Panigrahi is interesting. Of course, there are maybe 20 more versions of these things, but these are the major things, I guess. I don't know. Maybe they're more important, but these are major works: Chandra Chikuri, Jason Lee, Anupam Gupta, Thorup, and Panigrahi. And all of them are inspired by either David Karger or that guy in Maryland, I forgot his name, and that's it. So you will see that. So you will see how to use. The work of Karger, if we want to understand it, we should understand the why data structures. For example, Microsoft has millions of nodes, if we don't say billion. So we start from one vertex and we go. It is we don't care about who is the root of this tree. For example, we just pick the root randomly. And then we create a data structure. For example, a binary search tree. And of course, splay trees is a better data structure. And using the importance of data structure is that we can quickly calculate those spanning trees, because in the packing, you have to create many spanning trees. Each spanning tree gives us just a little bit interesting things. So an interesting and structural way to create those random trees are nowadays by these data structures, these dynamic trees, because you can delete it, we can update it, and you can insert it. Very fast, for example, in log n, in binary search tree. And because anytime, so you can use sampling tools, sampling paradigms. For example, you just sample some nodes, and after so you can find some distributed algorithms, and do it in a parallel way in order to maximize the speed of your algorithm, especially in the era of big data, that many paradigms, really, such as those LP relaxations, it doesn't work in Microsoft, it doesn't work in Google, because they cannot scale an SDP. Especially LP is even smaller, even is simpler. SDP, for example, how can you solve a big SDP? So that's why we need practical algorithms. These near linear time algorithms defined, that is done by Jason Lee, that is done by David Karger. And remember that David Karger has two major algorithms. First, the first one is based on the paradigm of contraction. It is we can use it for both min cut and multi-way cut, because we can stop when we have k edges left. And also another big paradigm is just dynamic tree. So they use the dynamic programming in order to create, in order to handle those tree packings in a very systematic and fast way. And that's why all of the work of David Karger, that's why it is near linear time algorithms. And many people still try to use the work of David Karger. For example, they change their data structure just a little bit, and this is their creativity. Because even if you make it just an epsilon better than the previous algorithm in terms of running costs or anything, just even the probability of finding all those min cuts, because you have many min cuts. It's not unique. It's not one of them. We have many min cuts, so the probability of finding them is higher and higher if your algorithm is more mature. But Chandra Chakuri, I like this researcher very much. I think he is in Georgia, but his work is very interesting. He understands, and he has created much structural and much insightful approaches to those K-cut. For example, he relates it to K-cut Steiner tree. And so he relaxed it and improved the paradigm. And that's why I like his approach. In 2008, for example, he wrote an article about Steiner K-cut. In 2018 or 2019, he improved that article. So the work of Chandra Chakuri in 2019 is just a modified and improvement of the work of David Karger, Michael Thorup, and many of great researchers. Okay, so have a great weekend.